Hi, we're Group 90 and we're presenting our oil and gas project. To start with the motivation of our project, predicting oil production output is important for operators for their investment decisions. So in this project, we aim to predict cumulative oil production for about 6,000 wells operated by 65 oil companies over a 12-month period using predictors such as well depth, oil in place, among others. This figure provides a quick snapshot of how the oil production works. And with this, our project was structured into 8 parts. First, data pre-processing, and we implemented 7 different models to investigate the most optimal model for our prediction. Benito?
Thank you. We use a data set of 6,080 observations and 23 variables. Some data points are missing in 13 of them. We drop one of them, reservoir thickness, which means over 57 data points. And we use the multivariate imputation with chain equations, aka mice, to impute the other predictors. We did one-on-hot encoding on 2 categorical variables in the dataset, reservoir and operator. Here is a description of the MAS procedure. It is a very innovative and advanced technique for handling missing values in that it accounts for uncertainty by using multiple random possible values and pulling them together to have a final imputed value for each missing data point. One key assumption for MAS, though, is that data are missing at least at random. More information is available in the report regarding the MAS procedure. Thank you. Mafe?
Here are our basic models. We choose multilinear regression as a start point to compare with other models. For the regularized models, we choose rich and lasso with cross-validation because we want to minimize errors and preventing overfitting and underfitting on base of a linear model. R-squared is being used to compare the performance of our models because MISEs are too large and adjusted R-squareds might not be appropriate for tree-based models. We use standard scalar and calculate the mean of R-squared from 10-fold cross-validation for different lambdas. The results are on the right corner, and the top 8 important features are similar for ridge and lasso. Christ.
After that, we decided to switch to tree-based models because we thought they had some advantages that were useful for our data set and our problem question. For that, we first fit on a single decision tree and then a random forest model, then an extra tree model, and then I identified the optimal tree depth with cross-validation, and then we further fine-tuned the hyperparameters with grid search. A little bit about extra trees. They are a variant of random forest with the difference that cut points for splitting are chosen at random and not by optimum. And also they do not use bootstrap samples, instead the entire original data set. The idea is to add additional randomness to further reduce the variance. They're also less computationally expensive and that allowed us to increase the number of estimators. And here you can see the results of the cross-validation for tree depth, and down here how the tree-based models compared to our baseline model. You can see that the extra tree regressor performed the best with a testing score of 0.5042. Shall we?
So for XGBoost, what's the rationale? Actually, we want to use the power of sequentially training submodels based on the previous mistakes. And empirically, it's the best performer for tabular data based on what Pavlov said in class and other benchmark tests. The challenge, of course, here is to tune the hyperparameters efficiently given the limited time. We actually narrow down the hyperparameter set. And in addition, we also use the multi-CPU to speed up the grid search CV process. Based on the cross-validation score, 7 is optimal depth, and you can see the other optimal hyperparameters here. Compared to the other models, XGBoost has the highest testing score with a small edge over extra trees. Optimal depth is much smaller than random forest and extra trees. And here you can see how early stopping works in the training process. In order to learn more about the models, we actually look into the permutation feature importance, just showing lasso versus XGBoost for simplicity. For lasso, we can actually see the negative importance in proponent intensity, which is counterintuitive, and the magnitude of the importance decreased pretty fast, and error terms are relatively large compared to the importance of the absolute values. If you see XGBoost, still the top 2 features are the same. However, all the top importance values are positive, and the magnitude of the importance decreases slower. Error terms are also smaller. Done?
To summarize, our final model was chosen based on the performance comparison across 7 models, and XGBoost showed the best performance on the test set, with extra trees being a competitive second. The innovation in this study was the usage of mice imputation to fill the missing values and the employment of extra trees with better performance in variance reduction and prediction compared to random forest. Also, we explored hyperparameter tuning for a more thorough exploration of XGBoost. Still, there are some rooms for improvement, such as feature elimination using tools like MRMR, combining multiple XGBoost models with different hyperparameters, incorporating time variables in the prediction. Thank you.